Our next presenter is Matt Bekker. He is an associate professor in the Department of Geography at Brigham Young University in Provo. Matt's work focuses on dendrochronology applications across the field of ecology.
Thanks. Thank you. It's green, but it doesn't. Okay, it is working, huh? Okay, good. All right, thanks to Darren and Justin for opportunity to present, and thanks to all of you for sticking around. Despite the couple of hour drive for me, it's always good to have an excuse to visit Cache Valley in the fall, so it's good to be here. I'll be talking about tree ring reconstructions of extreme drought for the urbanized Wasatch Front here in Utah, and look at it for those of you who aren't from the area. 80% of Utah's population, rapidly growing, and all very heavily dependent on snowmelt streams for both urban and agricultural use. Regarding the theme of the conference, I won't be addressing drought explicitly as a disturbance agent or an agent of change, but you've already seen several examples in this conference of connections between extreme droughts and forest conditions, and that might be through direct influences on mortality, through fire, through insect outbreaks, or even beaver. There's all kinds of interactions where droughts might make a difference. So definitely some interactions that I hope you'll be able to see. Also need to mention at the outset that this work is part of a much bigger effort by the Wasatch Dendroclimatology Research Group, the WADR group. Number one rule of success is you have to have a catchy acronym, right? So we're the WADR group, and we're all united by multidisciplinary, multi-institutional group, very diverse backgrounds, different interests, different skills, but we all have this common goal to better understand variations in water resources across many scales. And you heard from Simon Wong yesterday, one member of the group, and of course Justin DeRose is here as well. An outline of my talk. I know some of you are very familiar with dendrochronology or tree ring science, but for those of you who are not, I'll give a little bit of background. And then I'll talk about my work on reconstructing stream flow for the Weber River, one of the major rivers serving the Wasatch Front. And then I will very briefly discuss the reconstruction of the Great Salt Lake levels that Justin DeRose has headed up to demonstrate a broader view of variation in water resources in the region. So two key principles behind dendrochronology. First of all, cross-dating. We don't just count the rings. You have to visually and statistically match the barcode-like. It's not as simple as a barcode, two different cans of food exactly the same. But individuals of the same species in the same area will have roughly the same pattern of narrow and wide rings. And by matching up those patterns, first of all, allows you to know that you've done the dating correctly, that you haven't gotten off by a year. And dendrochronologists get pretty excited about annual resolution, and if you get off a year on the dating, then you no longer have that annual resolution. So you have to be able to cross-date just to make sure that you've got that calendar year is assigned correctly to that ring. But it also allows you to extend the record further back in time by incorporating deadwood, matching up the patterns of the narrow and wide rings with this deadwood, with living trees, can extend that record further back in time than would be possible with living trees alone. Another key component, key principle, is limiting factors. In a given area, there's typically going to be one factor that is most strongly going to control tree growth, and that will thus dictate the width of the annual rings. And in the arid and semi-arid Intermountain West, moisture is that most limiting factor. So a dry year leads to a narrow growth ring, and a wet year leads to a wide growth ring. So here we have 1977. This is from a Douglas fir sample in Colorado. Very dry year in 1977, and an exceptionally wet year in 1983. It's also important to note that while tree growth will respond to summer precipitation, that summer precipitation is not a very efficient source of moisture for the trees, but rather it's the snowpack prior to the growing season that is the key determinant of ring width. And the sample shown here is particularly apropos. 1977 has been called Utah's wettest drought. Very, very low snowpack the winter of 1976-77. Then the summer of 1977 actually had higher than average rainfall. But the trees didn't record that. That moisture didn't do them very much good, and that precipitation doesn't do us as much good either in terms of the water resources that we need for agriculture. It's that runoff from the snowmelt that's really critical. So it's convenient that the tree rings can tell us about critical water resources, both for humans and, again, also stresses on our forests. Well, this relationship between stream flow and tree growth exists because both of these will integrate the effects of precipitation and evapotranspiration. Again, in many cases, it's the winter snowpack that is particularly important to both water year stream flow and the antecedent soil moisture conditions upon which the tree growth relies. So we're not arguing that stream flow down here is affecting directly the trees up here, but they're both integrating precipitation and evapotranspiration. And we take advantage of that relationship to tell us something about past variation in water resources. So these tree rings can provide a much longer view of variations in moisture availability and give us a more complete view on extreme events in the system. For rivers in the Intermountain West, we have at most about a 100-year record of stream flow variability, which, as you can see here, for, wrong button, Colorado at Lee's Ferry is not a very extensive record. And we might look at this little 104-year record and say, oh, that's an unprecedented event. But as a colleague of mine said at a workshop last year, the tree ring record is where unprecedented events get their shirts taken off. You really get a better picture of unprecedented events when you have a several hundred or thousand-year record. Is that unprecedented? No, it's extreme, but it has been. Individual years like that have been seen before. With a tree ring reconstruction, we can see that. We can also see extreme dry periods, and I'll show you some more of those with the Weaver River reconstruction. So we get a better basis for risk assessment, and again, we can better understand the stresses in our forests as well. So, what's the tree ring record like in Utah? Well, this is a map of the Bonneville Basin, outlined in gray, and also shows the available tree ring chronologies in the region, so tree ring data sets. The black circles are freely available to the public via the International Tree Ring Data Bank. And you notice that all those black circles are, for the most part, outside of the Great Basin, or the Bonneville Basin. And the big hole here in the Bonneville Basin, especially around these major rivers, where we would most like to have those tree ring resources. There's also a couple of unpublished chronologies, these black diamonds here that we've been able to get a hold of. But our group, our first goal was to fill in this Bonneville Basin with all the tree ring data that we can. And these red triangles show the progress that we've made to date over the last few years, actually the last several years. Most of it's been within the last few. Trying to concentrate on these streams surrounding the big metropolitan areas, and then also trying to move out west into the little island forests that are there, and then eventually we'll make our way towards the south. So we're making some progress on filling that in so we can have better spatial and temporal coverage of tree rings to better give us a better understanding of spatial and temporal variation in water resources. In order for those tree rings to be valuable, you can't just go out and sample any tree. They need to be sensitive to moisture, first of all, and also as old as possible. Again, longer record is what is really valuable. Fortunately, we've been able to find a little bit of both, some old trees and some moisture-sensitive trees. Unfortunately, the really old ones, the bristlecone pines and the limber pines, are often at very high elevations, and sometimes will give a little bit of a squirrely signal, kind of moisture, kind of temperature, and sometimes they're only marginally useful. But we have some very good chronologies built from very moisture-sensitive species like pinyon pine, ponderosa pine. We have pretty solid sample depth back at least 600 years with the potential to go back much further. So with that background in mind, my goal was to try to reconstruct flows for the Weber River, one of the major rivers for municipal and industrial use along the Wasatch Front. I chose the Oakley gauge, this circle right here, because it's high enough in the watershed to avoid some of the really major diversions and reservoirs, The only exception being Smith and Morehouse right on that little stem right there. But it's high enough in the watershed, or sorry, low enough in the watershed to pick up the major headwater streams in the Uintas where most of the moisture is coming from. So kind of ideally located, and it also conveniently goes back about 100 years. There's lots of gauges on these different streams, but a lot of them are quite short. And as much time as it takes, as difficult as it is to gather good tree ring data, it is that much worse to gather good, clean stream flow data with no diversions, no dams, no reservoirs, and so on. With Smith and Morehouse, it's a pretty small fill and spill reservoir. You aren't going to be loading that up and then gradually letting it out over years. And it was expanded in 1987. I did compare data, correlation with stream flow before and after that reservoir was expanded in 1987, and there wasn't any significant difference there. Again, that's not surprising because I'm using water year stream flow, and so those small seasonal changes in the reservoir aren't gonna, they're just gonna kind of work out in the wash, no pun intended. Okay, so that's the gauge and also tree ring data. I considered all of the chronologies you saw on that previous map as predictors in a model of stream flow. So I had a whole bunch of options, but then I screened those according to their strength with Weber River stream flow correlation, and also the length of the chronology. Basically, my stipulation was that the data had to extend back to at least 1450 and up to at least 2005. I wanted to use as much of the gauge data as I could, and also wanted to be able to extend the record back as far back in time. So that left me with these 4 chronologies, 2 of which are part of the water effort to develop new chronologies in the region, and these 2 are existing chronologies from the International Tree Ring Data Bank. 3 are from two-needle pinyon pine, and 1 is from Douglas fir, both very moisture-sensitive species in the area. Okay, so I used principal components analysis to extract the major modes of variability from those 4 chronologies, and those major modes were then used as predictors of the gauged record of stream flow. And the model and instrumental water year flows are shown here. The full model explained, adjusted R squared, explained 54% of the variance, and passed all of a big suite of very rigorous standard calibration and verification tests. Very briefly, this procedure is, it's nice to have a good 100-year record like this because then you can cut it in half and use the early 50 years to calibrate a model and then use that to verify against the later data. And then you can do the same thing in reverse. Build a model on the outer portion of the data and verify that on the inner portion and see how it does. You can see that we did a little bit better with the calibrating on the outer portion and using that to predict the inner portion. It's pretty common in tree ring reconstructions of stream flow, probably because the instrumental record is a little bit more iffy as you go further back in time. But in all cases, we were able to pass the tests, and also just looking in comparing the instrumental with the reconstructed data, the really extreme years, the most important ones like 1934, 1977, 2002 there, show up really well. They were estimated really well with the model, as well as these low frequency trends, both for wet and dry periods. Okay, so the visually does a pretty good job of matching the observations, and also statistically passes all the tests. So here then is the full reconstruction. It extends from 2005 back to 1429. The blue line shows the individual years, again, water year stream flow, and then the black line is 11-year running average to give you an idea of lower frequency trends. The gray box here is the area where one of the 4 chronologies, the sample depth drops low enough to be below a generally agreed upon threshold of what's called the express population signal. And so the reconstruction is a little bit less reliable before that time. I'm going to go ahead and present all of the data, including that gray box, but just know that anything before about 1480 is a little bit less reliable. Okay. You notice from this full reconstruction that we have indeed had some pretty extreme years in the instrumental record, 1934, 1977 again, being very notable. but that they have been exceeded by some of these back in the 1500s and 1400s. So 3 or 4 different ones that are worse than 1934. And you also notice, following the black line, that we've had some periods of extended drought. For example, the early 1700s right here, and the late 1800s right here. A couple of years above average in between all of that, but a pretty extensive section there with no individual years above mean annual flow, and completely unprecedented in the instrumental record. Nothing to compare to those types of droughts. This graphic emphasizes some of those persistent droughts. So this is only showing droughts where there were at least 2 years in a row that were below mean annual flow. So the horizontal line stays that way anytime it's above average, or if we just have 1 year that drops below mean annual flow. Every time you see a drop here, there's at least 2 years in a row there. And you can, again, pick out some of these extensive droughts, early 1700s, the late 1800s, and also, again, some pretty high magnitude areas where we just had 2 or 3 years that were below average. Perhaps a ranking of some of these extreme years and longer periods will help. These are the most extreme dry years, the 5th percentile of dry years in the record. And I have the instrumental years included in bold. So 1934, 77, and 2002 all made it into that lowest 5th percentile. But if you look by century, the 1900s actually had the fewest of these extreme dry years of any other century. And definitely 1500s and 1400s had some worse individual years. So based on extreme individual years, the instrumental period has been relatively calm. But what's really critical are these long periods of drought, the kind that can really strain water resources and also impact our forests. This table shows a ranking of the 25 worst dry periods in the Reconstruction, and they're ranked based on a score that includes the magnitude, which is the cumulative departure from mean annual flow. So 9 years, if you add up all of the total amount of flow below average, that's what you get. And then divide that by the number of years and you get the intensity. And then these are ranked based on the score. That's a combination of those two statistics. So again, we see some pretty bad droughts in the instrumental record. 1930s, late 1950s, early 60s, and early 2000 to 2004. But we also see that there have been several droughts that exceed anything that we've seen in the instrumental record. Again, particularly during the 1400s and 1500s. And not only in terms of the overall score, looking at the different magnitudes and different intensities, but if you just look at duration, 1703 to 1718, we had 16 straight years with not a single year above mean annual flow. So nothing to compare with that in the instrumental record. Another thing I noticed in looking over those data in the previous table is those were just periods of consecutive drought, not a single year above average. But I also noticed that we'd have a drought several years in a row, and then just 1 year above average, and then another several years in a row below average. Well, from a management perspective, if you have several years below average, then just one above, and then several more years below, that 1 year above might not be enough to fill your reservoir. That 1 year above might not be enough to allow a forest stand to recover from the effects of the previous drought. Might leave it susceptible to insect outbreaks or so on. So here I have clusters of smaller droughts that are separated only by individual years above the mean. So there might be more than 1 year total in the cluster, but what we have here are 4 different droughts that are separated by individual years in between, if that makes sense. Okay, you can see the different groupings. And then I've, again, ranked those according to magnitude, intensity, and an overall score. And so we have 14, 18, 15, 11 years of these droughts with just an occasional blip above the average. And the only thing to come close to that in the instrumental record is 1953 to 1961, 1957 was a wet year. But actually, 1930 to 1936 was 7 years long, and was consistent. No years above average there. So if you're going to look at the instrumental record to try to get sort of a design drought, the 1930s are probably the best one to use. We certainly have had some periods where very extensive, long drawn-out droughts without much of a break at all. Well, I mentioned at the beginning that our group is interested in understanding spatial variation in stream flow. So how does the Wasatch Front compare with the broader Intermountain West, and why? Well, this graph shows the Weber River reconstruction compared with the Yampa, and this is a tributary in the upper Colorado River Basin. And you'll notice some periods where they agree very, very closely. And one of those is in that early 1700s drought, almost exactly, that 1703 to 1718. I think they were 1 year different. Also similarly here in the late 1800s, but some others where they diverge quite a bit. I've also compared, I don't have the graphics here, but I've also compared that with the Spring Valley in Nevada and the Snake River in Wyoming. There have been all these reconstructions all around Utah, and there's this big hole here. So we're finally filling that in and making these comparisons across the Intermountain West. And we see some evidence for west-wide droughts. The entire Intermountain West probably had extreme droughts at some periods. In other cases, they were regional or maybe local. And again, this is important for water management to know, how many different river systems are being affected. And again, with the theme of this conference, how much of a forest is being impacted. Is it regional? Is it very, very broad scale or more localized? Okay, and again, this emphasizes the need for further investigation, more chronologies for us to work on next summer, try to fill in some of the holes there and find out just how extensive these droughts are throughout the West. So in conclusion for the Weber, there's considerable variability in the system, and our instrumental droughts have been exceeded several times, both in terms of individual years and more extensive records, more extensive periods. We take, for example, 2012 to 2013. It's been dry the last couple of years. 2012 is roughly comparable with 2002. If we go back to this table here, well, let me just mention a couple more things. The overall magnitude for the 2 years, 2012 and 2013, was minus 4.9, and the intensity, minus 2.5. When the Reconstruction, we saw droughts that intense that lasted much longer than that. Okay? So a little bit lower intensity here, it lasted for 9 years. Okay, this next one, actually higher intensity than 2012, 2013. It lasted for 4 years. And then once again, 1703 to 1718, relatively low intensity, 2.5 for 2012 to 2013, 1.29 for here. So about half as intense, but it lasted for 16 years. So if we look at the Weber River, our reservoirs right now are at about 50% capacity. So let's say these last 2 years were only half as bad as they really have been. Then maybe we get 2 more years before we get down to 50% capacity. Well, we've still got 12 more years to go before we start filling those reservoirs again if we have an event like 1703 to 1718. So all this highlights that our instrumental record, our gauged record, is insufficient to really be able to establish a basis for an assessment of the risk of drought. And once again, related to the health of our forests, we need to have a broader perspective to be able to understand what kinds of conditions they might face. So our hope is that water management agencies will be able to use the data that we've provided to have a better assessment for risk, and hopefully we'll be able to do that same thing for forest ecology. And let me just quickly make some comparisons with Justin's reconstruction of the Great Salt Lake. We have a little bit longer record, go a little further back in time, and both for elevation, and we can also look at the elevation change from 1 year to the next. For several reasons, it was actually better to use this for the reconstruction, but a similar model using the chronologies that we've developed from the region. We were able to have a successful model of the Great Salt Lake. Once again, look at where both the droughts and the pluvials were the really wet periods, really dry periods. and then make some comparisons with the Weber River reconstruction that I've talked about, and also the Logan River, which Tammy Rittenauer, Utah State, and her student have worked on recently as well. And once again, this allows us to take a look at, regionally, where was this drought the worst? Was there more water coming into the Great Salt Lake through the Bear via the Logan, or was the Weber a relatively more important contributor? This gives us a better spatial picture of droughts in the past, and also, as you saw from Simon Wong yesterday, it also allows us to get a better idea of, by comparing these variations with what's going on out in the Pacific and then trying to make some connections with climatology, we might actually be able to do some better forecasting in the future of when the droughts are going to be and when the floods are going to be and so on. That I'd be happy to take any questions. And by the way, I always get the question, where is this? I cheated, it's not in Utah, it's in Glacier National Park. So here's hoping for a good snowpack for this year. Any questions?
Given your analysis, and if hypothetically you're a water manager, what do you recommend on doing? Increasing storage?
Yeah. Well, so it's a good question, and we've been discussing that over the last week. We just had a meeting with water managers last week, and the question is, how are they going to be able to use the data? And that's really going to depend on what they're prepared for to begin with. How have they already been assessing drought? And some water management agencies are more sophisticated than others. Some are ready to take the data and chug them right into a forecasting model. Others have just used analog, what's happening this year, what might happen next year, and so on. So I guess there's not really much I can say by way of suggestion because it's not something I've ever worked with. I'm not a engineer or fluvial geomorphologist who's kind of trying to think about any of that. It's been really interesting to me to meet with water managers and see what's valuable in terms of scientific data and what isn't valuable. And it was kind of funny, one of our very first meetings with them, all they said was, we just want you to tell us, is it going to be dry next year or is it not? And by the way, if you can tell us when the earthquake's going to be, that'd be great. And it was interesting because I was actually able to tell them I've used tree rings to reconstruct past earthquakes, so maybe we might be able to help with that. But yeah, that gap between the science and the application is difficult sometimes. And we're trying to bridge that, and a lot of communication to have to take place for that to really do some good. Yep.
Matt, you said that you're going to be, I think you said you're going to be working south, so do you have a project plan for the Severe River? And timetable, what you think you might, that would be a significant impact on much of the state.
Justin, can you comment on that? Timetable?
We have a preliminary reconstruction on this.
You started on the roof.
Yeah. We just need more sharing data.
Yeah.
Crystal comments preferable.
Yeah, that would be great, wouldn't it? Good point. That day is probably the closest to death I have ever been. I was not a very good skier. I had a heavy pack on. We had 2 feet of fresh powder. I almost didn't make it down off that mountain. So, yeah, a hat and other preparation probably would have been good.